So in this unit, the whole purpose is, as we see, making inference about these variables. And some of what I want to discuss today goes back to the beginning of the year. Because statistics is a process. It's not just like this section or this section. It's an entire process that builds upon itself with a purpose. And we're finally arriving at that purpose of being able to make inferences about a set of data. So to begin this process, you need to produce data or collect data. And the basics here, I mean, we know that we're working with individuals or subjects. Those are the people that we're typically working with. And these variables can be either categorical or quantitative. Again, categorical, there's a label to that data. Quantitative has a numerical measurement. And typically we're comparing the means of those quantitative values. So the purpose of this is in the design. Okay? We have the observational studies and the randomized experiments. We talked a lot about that in the first semester. It's starting to come full circle in what that difference indicates with our conclusions. Remember, observational study, you're observing the participants in their existing environment. Observing them exhibiting their natural behavior. And you have less control in the observational studies. While with the randomized experiment, you are now assigning treatment to those individuals. You have that control. So the possibility of causation is the big implication for the randomized experiments that you cannot get with the observational studies. So now, when we're talking about a p-value being less than 0.05, and we have a significant difference between our two variables, if that's from a randomized experiment and that p-value is low enough for you, you have evidence that this explanatory variable is actually causing that change in the response variable. You cannot say that with the observational studies. When you lose that control and you let them exhibit their natural behavior, well, these variables tend to cluster together, and there's other attributes that could be influencing your results that you do not have control over. So again, maybe they are influencing or they are causing that change. So the best you can say if you have a low p-value in an observational study is that there's an apparent relationship between these two things, okay? Or even a strong relationship between these two things. We know that the randomization really helps us with the selection of our sample. It helps us with the assignment of our treatment in the randomized experiment. We put a lot of trust and faith into that randomization. And over these next few slides, you'll see some of these beware bullets. Okay? We've talked about a lot of things over the course of the year that we need to watch out for as part of this process. Here it's talking about being aware of poor sample selection, whether it's a voluntary response or a poor method in that this sample does not represent a larger population that you're trying to describe. In general, if you have bad data coming in, you're going to get a poor analysis coming out. Now, it seems like we've been doing a lot of data analysis, but this really initiated back in September when we had a visual analysis with the displays of data, with a graph. Okay, the categorical values can be displayed with the bar graphs, the pie charts. The quantitative data can be displayed, stem plot, histogram, box plot, that sort of thing. And we accompany with that with the descriptive statistics. Okay, so that's starting to give us an idea about the pattern, the shape, extreme values that are possible outliers affecting our conclusions about this data set. When we're comparing two quantitative variables, we're looking at the scatter plot, which sets us up for correlation and regression. We are not done with regression. One of our remaining 3 chapters in our last unit deals with a significance test with regression to test to see if we have a significant correlation with our values here. We know that outliers can influence our interpretations of our results there. Now, this all leads to what we're currently talking about with inference. We are trying to use our sample to infer something about a larger population. And one way to do this is with a confidence interval. We know that the confidence interval allows us to create a range of possible values that we're pretty sure that true actual value falls between in the population. Again, I've said this before, that we don't directly care about our sample. Right? The sample is a means to an end. We don't want to do a full-blown census and look at every single person in the population. So instead, we're using our sample to say something about the population. So a confidence interval helps us with that, not by getting a single number that matches that population value, but it provides us a range that we're pretty sure, 95% confident, 99% confident, whatever, we're pretty sure that actual population parameter falls between those 2 numbers, whether it's a proportion or a mean. Remember that the margin of error, the whole reason for that interval is for the sampling error. It's not to overcome poor sampling techniques, or bad data. And it's purely just for the natural variation where, again, you flip a coin 100 times, you expect 50-50, you get 55-45. That sort of variability is the sampling error. It's not for getting like a bad sample, and that's not included with that boundary. The other inference that we have is a significance test, a hypothesis test with these null and alternative hypotheses. We spent some time yesterday talking about the difference between a 1 sample and a 2 sample significance test. With the 1 sample, whether it's a mean or a proportion, we have some value. Okay, we have a value here. We're saying that this is equal. Yeah, who cares about that? It's some form of equality with the null hypothesis, saying it's equal to some number. Let's just say mu is equal to 25. With the 2 sample, the null hypothesis is comparing to another sample. Okay, so there's no null value there. You're testing to see if there's a significant difference between those 2. And as we work our way through, we're getting a test statistic that corresponds with a p-value. That test statistic, it's a t statistic if we're working with means, because it's not practical for us to have a population standard deviation. If we're working with proportions, we're still using that z model because we don't need the standard deviation there. Now, what the p-value is a probability. It's the probability that that null hypothesis is true, and we expected to get this, but we got this. It's the probability that that could happen, that difference could happen, just due to natural variation. Okay? The sampling error that we just talked about with the margin of error. If we have a 12% probability as our p-value, that's not that rare that we would expect this and get this. So at 12%, we believe that the null hypothesis is true. Okay, 12% of the time we're getting this far away from what we expect, not that rare. But if we have a p-value that's very small, then we're saying it would be incredibly rare for us to expect this and get this just due to natural variation. We got this probably not because of natural variation, but because we have some significant relationship here, that this null hypothesis is not true. So we reject that null hypothesis and accept the alternative, that it's different from what we expected, or it's significantly greater or less than what we expected. And our sample is the evidence of that. Now, we're typically comparing this p-value to 0.05. We call that the alpha level of significance. There is nothing sacred about that number other than that it's a convenient balance to our 95% confidence interval, which we had said was within 2 standard deviations on our normal distribution. Okay? It's a good compromise between width of the interval and level of certainty. We've seen many cases where 5% is not rare enough. Okay? If you had a p-value of 0.04, yeah, on that level you'd reject the null, accept the alternative, but maybe 4% is not rare enough. We've seen some problems where our p-value gets really, really small, but the calculator gives it back to us in scientific notation. That sort of significance tells us that there's a very strong relationship. All right, so when you're doing this inference, talks about choosing the right inference procedure. That's what we had talked about yesterday with our chart. Okay. Is it a significance test or is it a confidence interval? Is it 1 sample, 2 sample? Is it means? Is it proportions? Okay. Carry out the details. I mean, those 4 words, there's a lot that goes into that. But that's the actual procedure, the calculations, and then stating your conclusion. Our conclusions are not just ending with we reject the null or we fail to reject the null. Sometimes we get into that habit, like when I'm doing problems in class or when you're doing problems in your homework, problem after problem, we just kind of end it right there. But really, you want to bring this back into the context of what's going on in this situation. Why did you start out doing this problem in the first place? Okay? We're going to see how that's really important as we do these projects in labs, okay, over the next several weeks. So here's that flow chart that we had discussed. Again, confidence intervals are on this bottom branch. You're using those to estimate a population parameter, whether it's a mean or a proportion. This top branch is kind of what we concentrated on yesterday and what we'll continue to be working with today. This identifies the correct procedure, either 1 or 2 sample, proportion, or mean. Okay? Quantitative or categorical data can help you answer that question. Again, you may want to write down the number of the command for the calculator or what that command is on GeoGebra on this sheet. Okay, so for what we're working with right now, again, we talked about categorical or quantitative, indicating whether we're using T or Z procedures. Again, T is for means, Z is for proportions for what we're working with. The inference for a single mean. Again, our null hypothesis here is that we have some value. I had said 25 for some reason there. 25 is our anticipated average. One of the things that we'll be looking at with these t-tests is that possibility of a paired t-test. Now, we had previewed this a little bit. A match pair design experiment is when you're either subjecting the same individual to multiple treatments or 2 similar individuals are pitted against one another. And the way that works is you're taking 2 samples, but you're finding the differences between those values and analyzing them with 1 sample procedures. We had done an example with a chimpanzee trying to find that food, either by getting the help from another chimp or trying to do it on their own. And they had two sets of data, but what they looked at were the number of times they got help minus the number of times they tried to do it on their own, and that new set of differences is what they analyzed with their one sample procedures. Okay? So we have the possibility of doing a paired t-test when we do this ping pong ball lab on Monday. Okay? We'll talk a little bit more about that possibility coming up then. You don't have to do it that way though. With the difference of two means, again, now your null hypothesis is that mu1 is equal to mu2, that there's no difference between these two sample values. They are the same. Your alternative is testing to see if they are different or one is significantly bigger or smaller than the other. With the proportions, same thing. Single sample, you're testing to see in your null hypothesis, where your null hypothesis is stating that that population proportion is some value. A lot of times it's 50% to test to see if we have a significant majority or minority. Okay? You take your single sample, is that percentage significantly above or below, or just different? One possible example, I can't remember if we've actually discussed this sample, was a study that was done about 30 years ago where they were testing to see if people had like psychic abilities and they were able to telepathically communicate with other people. And one of the ways they tested this was they had 4 choices, and the person in a different room was supposed to receive a telepathic communication about which of those 4 choices was selected. So the null hypothesis, just by guessing alone, they were to get it right 1 out of 4 times, 25% of the time. But when this person was kind of sending what that correct answer was to them telepathically, they were testing to see, for the alternative hypothesis, if they would guess it significantly more than 25% of the time, and see if this was significant evidence that they were actually able to communicate this to them. Now, I think, if I recall the experiment correctly, the sample proportion that they got was like 33%. They expected to guess it 25% of the time. They actually ended up guessing it 33% of the time. Is that strong enough evidence, far enough away from what you expected, to be convinced that it was telepathic communication? I don't know. I forget what the sample size was. Okay. But you can kind of see how you would set that sort of a test up. Lastly, with the 2 sample proportions, your null hypothesis here is that proportion 1 is equal to proportion 2, that there's no difference between how like a young group would answer these questions versus an older group, or males or females answer these questions. This is where you can get an interesting analysis of survey data, because you can compare different subsets of the population against one another with these 2 sample Z proportions. All right. Any questions on this? Okay. So let's go back to those problems that we had looked at yesterday, where we were just purely identifying what type of test we're using. Maybe we'll do like 2 or 3 of these together and just see what that procedural calculation looks like. So this was our first one from yesterday. It was people who were against replacing the $1 bills with the $1 coins. And we had said that this was a 1 proportion Z-test. one sample z-test, one proportion z-test. Okay, and the key words here, statistician read that at least 77% of the population was opposed to replacing the $1 bills with $1 coins. Okay. So our null hypothesis here, we have that population value, 77%. The null hypothesis is always a form of equality. Okay, so we could say P equals 0.77. But I'm going to go out further here and say, because it says at least 77%, I'm going to make this greater than or equal to. And this is going to help us with the direction of the alternative hypothesis. Because in this alternative hypothesis, if they say what's expected is at least 77% is against it, then that means that we think that we have evidence that it's not that big. And we're going to say that this population proportion is less than 0.77. To determine the direction of the alternative hypothesis, you need to read the question carefully. Okay? Usually that first sentence or that last sentence. And in this case, we only have two sentences. Okay? But usually you're going to have some key words there that say something like at least, or a difference, or maybe just outright say greater than. Something like that will indicate the direction of this. So we have a one-sided alternative hypothesis. Now, our sample value, p hat, we took a sample of 80 people, 55 of them were against it. And we did this ratio, we worked this out on the calculator, 0.6875. So we expected 77%. We got 68.75% from our sample. This test is answering the question, is this number significantly far enough away from here to say that we have a significant difference? So, going to the calculator, I'm not going to flip screens or anything, you know how that takes time. But on the calculator, stat tests, it's a one proportion z-test. So one proportion z-test, this is number 5 on our calculator. So we are entering this null value of 0.77, and we're entering our sample ratio, x and n, 55 and 80, and making sure that we have the correct direction for our alternative hypothesis. We determined that this would be less than. So go down to calculate. We need to give the test statistic and the p-value. So the test statistic is our t statistic. In this case, not t, z, which is negative 1.75. Okay, on this normal sampling distribution, where we expect 0.77 at the center, we are 1 3/4 standard deviations below what we expected. And that corresponds with a p-value of 0.039, I'm going to say 0.04, which is just barely below 0.05. Reject the null hypothesis. P is low. Reject the HO. Reject the null. Accept the alternative. So what that means is we believe this is true. We believe that there is significant evidence that that population proportion is actually less than the 77% that they claimed it to be. Any questions there? Let's maybe try one more of these. This study was looking at, remember, we were able to identify what test, not even through the first sentence here. It said a study using 2 random samples of 35 people each found that the average amount of time, we had said that this was a 2-sample t-test for means. And in this case, we're looking at the average amount of time that this 26 to 35 year age group spends on leisure activities per week. And we have an average value here of 39.6 hours for the younger group. For the 46 to 55 year age group, their average amount of time spent on leisure activities was 35.4. So we're given standard deviations 6.3 and 5.8 for those two groups. Can it be concluded that there is a significant difference in the average times each group spends on leisure activities? Okay. Here's the key word that helps us indicate the direction of the alternative hypothesis. So, null hypothesis. This average amount of time spent on leisure activities for this younger group, 26 to 35 years, we'll call it mu sub y, y for younger, that it's the same as the average for the older group, mu sub o. The alternative hypothesis, we're testing to see if there's a significant difference. That is an implication of a two-sided alternative. It's not saying bigger or smaller, just different. And I know what you're saying. You look at these two numbers. Obviously 39 is bigger than 35. But remember the order that this would occur. You're technically setting these hypotheses up before this data is collected. Okay, so unless you have a strong indication going into it that one is going to be bigger or smaller than the other, the safe way to go into it is with a two-sided alternative. So the mean for the younger group is not equal to the mean for the older group. Any questions there? All right. So back on the calculator, doing our test, we had said it's a two-sample t-test. Okay, so stat and tests. You just look on your screen there. Two-sample t-test is option number 4. So when you make that selection, you have two choices. If you had the raw data here, this probably would have been entered into L1 and L2 on the calculator. We don't have that. This is actually going to be easier. We want to go to the Stats tab and just feed the calculator these numbers. X bar 1, SX1, N1. So we have the mean. Okay, we're going to go the younger group as 1, the older group as 2, because typically we want to go big minus small. Okay, so big first, small second. So X bar 1 will be 39.6. Standard deviation for our younger group is 6.3. Sample size. The sample size of both groups is 35 separate people. So 35, X bar 2 was 35.4. Standard deviation for the older group is 5.8. And N2, the sample size for the older group, is also 35. Set our alternative hypothesis to not equal to. Leave it as not pooled, and then down to calculate. Here, our test statistic is the t statistic, so t equals 2.90. Okay. Again, same interpretation as a z-score value. On our new t distribution, we are 2.9 standard errors away, which corresponds with a p-value here, 0.005. Less than 0.05. Reject the null, accept the alternative. And again, our interpretation, I'm not writing it here, but it's just as important. We have significant evidence that there is a difference between the average amount of time that this 26 to 35 year age group spends on leisure activities in comparison with the 46 to 55-year-old age group. Any questions? So let's give you a little bit of time to practice some of these on your own. As I said, you have a non-graded review assignment. You know how they do a review chapter in the book. This is chapter 24. So we're looking at starting on page 564. The review assignment says 1 through 65. Yeah, I don't expect you to do 65 problems. Okay? I don't expect you to start with number 1 and go as far as you can. No, feel free to jump around. Look at things that maybe today you just want to get your feet underneath you and do some problems that you feel like you know how to do. I did link the answers to this assignment page. So that is on Canvas for you. You know my suggestion, don't just immediately jump to the answers, but practice these. Okay? Our test isn't for a couple weeks, but we want to get comfortable doing this. Okay? Getting good with this, it's going to help us with our projects. Hopefully those projects will help inflate grades too. No, wrong word. Redact that inflate. Boost grades. Okay? Help boost grades. All right. So, I want to give you some time. We got like 30 minutes that we can practice some of these problems. Okay? All right. Those of you in the classroom here, we got books on the side. You're welcome to borrow. Those of you online, yeah, please stay logged in. And if you have any questions, let me know. Okay, go ahead.